lecture, we're going to talk about something called the divergence. And the whole point is just to get a good conceptual understanding of what is meant when you take the divergence of a vector field. Okay, so in general, a good definition for the divergence is thinking about the amount of flux entering or leaving a point. Okay, so we've thought a lot about flux through a surface, but now we're going to think about how can we define flux through an individual point. Okay, so let's think about the electric field around a positive charge here. So I'm going to draw some vectors that describe this electric field. Okay. And over here, I'm going to think about the electric field around a negative charge. Again, I'm going to just draw some vectors that describe that particular field. And let me draw a little better. Okay, based on our discussion before, hopefully it would make sense to you that if I were to draw a tiny little box around each of these surfaces, or each of these points in the center of these fields, each of them would have non-zero flux. In fact, over here, there would be lots of positive flux through the box. And over here, there'd be lots of negative flux through the box. So that goes back to our definition of flux. And of course, if I were, by the way, to draw a box out here, okay, the flux through this box is zero, okay? And again, that's because the field is just passing through that box. There's essentially as many field lines coming in on this side as coming out on that side. Okay, there's no charge in that box. Gauss's law tells us the flux has to be zero through that box, okay? So that's how we can think about flux. We should be kind of familiar with that. Let's relate that to the divergence, okay? So the divergence is kind of like the flux per volume, okay? So I was thinking about flux through the surface, but now I don't want to just think about the flux through the surface of these boxes. I want to think inside the box, the volume of the box, how much flux is going through little bits of volume of those boxes. Okay, I say it's only kind of like that because the divergence is calculated at a point, okay, just like we calculated like the gradient at a point. So really what I want for the divergence is I want to think about taking a limit where the volume is going to zero of this kind of definition. So I'm going to take the flux over volume, but I'm going to shrink the volumes down to an infinitesimally small amount in order to calculate something that describes the flux at a single point. Okay, so that's what we want to think about when we're thinking about divergence. Okay, so let's look at a couple of other potential electric fields, or we can really do the divergence for any kind of vector field, so we can just think about these as general vectors. But let's say I've got an electric field that is pointing upward, but it's stronger. Okay, it's increasing in its strength as I go up the page here. Okay, again, I can draw my point here, and I could think about putting a tiny little box around the point, okay? And now I can think, can I reason whether the flux through that surfaces or through the volume of that tiny little box would be 0 or non-zero, okay? In this case, I hope it makes sense that we would have a non-zero divergence, okay? There's more flux coming out of this side of the box that's coming in over here, okay? And we've got some nice symmetry, okay? So there is, when I add up the total flux around this box, or at least inside of it, it's not going to be 0, okay? And I can't really say whether it's positive or negative, because that's going to depend on how I define a coordinate system. So I'm just going to leave that. But I know that it's not 0. All right. But let's think about another kind of vector field that doesn't change, okay, vertically or as we go up the page here. So this is just a constant electric field. I'll make sure it's clear that it's constant. Okay, in this case, if I were to draw my point, okay, put my little box around that point, and I want to think about how the flux is changing throughout that box. In this case, because it's a constant field, that means that flux per volume isn't changing. And so that means that the amount of flux coming in this side of the volume is equal and opposite to the amount of flux coming out of the other side of the volume. So that means we have a 0 divergence, okay? What if we had another example, okay? And in this example, we're in kind of a swirly field where our electric field or our vector field in general was just swirling around. And now I'm going to put a point right in the middle of this particular field, and I'm going to think about the flux per volume in this case. In this case, I'm going to argue again, there's still a 0 divergence, okay? And even though that the field is changing around the box, I'm going to argue that the flux per volume inside the box is still going to sum to 0, because if I think about the flux per volume in the box and that changing vector field, it's basically the little infinitesimal flux elements. The flux elements through the infinitesimal bits of volume, they're all canceling out. Okay, so I end up getting a total flux per volume that sums to 0. Okay, so the vectors are changing. So vectors are changing, but okay, the gradient or the rate of change in the x, y, and z directions cancel out. So that hopefully helps you get an idea about how you can think about whether the divergence in a particular field is 0 or not 0. Okay, let's actually figure out how to calculate it. Okay, so I want you guys to remember the vector operator del. Okay, and del is equal to, right, all of the partial derivatives, at least in Cartesian, in the directions times the unit vectors in those directions. Okay. We're going to use this guy again, right? This is for Cartesian. But let's remember what it does. It basically tells you the rate of change in all directions. Let's apply it instead of to a scalar field, which is what we did when we calculated the gradient. Let's apply it to a vector field. Okay, so when I apply this to a vector field, let me pick a vector first. So I'm going to pick something really general. V, you can think of it like velocity if you want. Okay, the three-dimensional velocity vector. Okay, if I apply it to a velocity field, what I'm going to do is I'm going to take the dot product of del, so this is the dot product, and I'm going to dot it with that vector, and so that's going to end up giving me, if you guys remember how the dot product works here, the partial derivative of that vector in each of the directions, but I'm going to end up with a scalar. So what I'm adding together here is I am adding together the partial derivative of each of the components of my vector with respect to the direction. So for example, I'm just going to take the function that describes how the x component of my vector is going to change, and I'm going to take the partial derivative with respect to x of just that component, and then I'm going to do the same thing with y and the same thing with z, and I'm going to add them all together. Okay. So this is a scalar, and it's common to kind of forget what you get out of these, but when you take the dot product of two vectors, you end up with a scalar. Okay, so one way to think about this, okay, in terms of, again, these kinds of problems, a different way to think about it, okay, mathematically is, okay, if your vector field is not changing in any direction, okay, then the divergence is 0. Okay, that's certainly the case here. If I think about this point, okay, the vector field, the components of my vector here in the x and y direction, they're not changing as I move left or right, up or down, okay? They're constant. It's always 0 this way, and whatever this value is, whatever the length is, it's the same up and down, okay? If it is changing in more than one direction, and I'll add a caveat there, the changes don't cancel out, okay, it's possible to have changes in the x direction that are equal and opposite to the changes in the y direction, okay, then the divergence is not 0, okay. If it's confusing because you're looking at a vector field and it's clearly changing, but I'm telling you that the divergence is 0, okay, or the math is telling you that, it's probably because the rate of change in one or more of these directions is canceling out. So when you actually calculate this, it may not be 0, but when you add it to this, right, they could sum to 0. All right, let's end this with a final definition for our divergence. Okay, it's the amount of flux entering or leaving a point, okay? So if I want to calculate it, I just wrote this, so I'm going to write it again, but it's going to look exactly the same. I want to take the partial derivative of the components of my vector in every direction, and I'm going to sum them, and I'm going to end up with a scalar value. Okay, so I want to make sure you guys remember that note. The result is a scalar, okay? And it's also important to note that this is evaluated at a point, okay? So the result could be a function of x, y, and z, if the divergence of a field is not uniform, but you would just plug in values for x, y, and z to figure out what the divergence is at a particular point. Okay, so the next thing I'm going to do is show you how to calculate the divergence with Mathematica.